and welcome to episode 8 of Maths in an Empty Classroom with me, Mr. Southern. Today we're going to be looking at hinges. This is continuing on the statics of rigid bodies topic, where we looked at uniform rods, we looked at ladders. We're now coming to consider what happens when you have something that is hinged at a point. And what it has is implications for the reaction force at that point, which we'll talk about as we work through this example here. So here we go. We have a uniform beam AB of mass 15 kilograms and length 3 meters is attached to a vertical wall by means of a smooth hinge at A. Smooth, again, as before, modelling assumption, no friction within the hinge. The beam is maintained in the horizontal position by means of a light inextensible string, one end of which is attached to the beam at B, and the other end is attached to the wall at a point in the wall 4 meters vertically above A. Right, so let's get this into a diagram. First of all then, we have a vertical wall, and then we have a uniform plank, AB. And then what we have going on is we have a light inextensible string which is holding that plank horizontally. So what we have is, this is the point A, this is the point B, and it's being held in place here, and we were told earlier on, or we were told in the question, that that distance there was 4 meters vertically above A. And then what we have at A is a smooth hinge, but I'll deal with that in a minute. Now, we were told that the plank is uniform, so we can say that its weight acts at the centre. I believe, if memory serves, that the mass was 15 kilograms and 3 meters. There we go, just so I didn't get that wrong around. Right, so we have 15G as a force there, and that is acting halfway along the plank AB. So it's 1.5 meters from the wall. So we've got the weight of the plank acting directly downwards, that's 15G. We also have a tension force in the string acting there on the plank, and we have a tension force acting on the wall. Okay. It's just worth labelling that actually, because some of our points later on will depend on that. So that is acting on the wall, and that tension there acts on the plank. Okay. Now, what's happening here? When we had a ladder, the reaction force at the point where the ladder hit was modelled as being perpendicular to the wall. Now, this doesn't happen here. And the reason it doesn't happen here is that A is not just a smooth point where something is resting. A is actually a hinge. And the point of a hinge, if you consider a door, is to allow things to turn. Now what that means is, if this plank were allowed to move, it would be turning. And the consequence of that is, it would be exerting a turning force within the hinge, and therefore the reaction force would not be perpendicular to the wall. So what we do for the reaction force on a hinge, or at a hinge, is we model the reaction force as having a horizontal component and a vertical component. Which I will call reaction X for x-axis, and reaction y for y-axis. So we have two components of reaction going on here because it's a hinge. You may be thinking at this stage, how did he know which way to draw those two arrows? I'll deal with that later on. So, let's just refer back to the question, check we've got all the information. A uniform beam of mass 15 kilograms and length 3 meters is attached to a vertical wall by means of a smooth hinge at A. The beam is maintained in the horizontal position by means of a light inextensible string, one end of which is attached to the beam at B, and the other end is attached to the wall at a point in the wall 4 meters vertically above it. And we're being asked to calculate the tension in the string. Okay, well actually, because this is statics, same rules apply. Resolve vertically, resolve horizontally, do some moments. Those three things are going to see you all right. So we're going to start off, we're going to be trying to find the tension that's in the string. And what I want to do to be able to do that is I want to take moments about the point A. And the reason I want to take moments about the point A is I've got an unknown reaction X, I've got an unknown reaction Y. So if I take moments about this point, I can ignore both of them because currently they're unknowns. So if I take moments about the point A, I need to consider which forces are trying to make the beam, the plank AB, rotate clockwise about the point A. So there's the point A. Which forces are trying to make it go clockwise? Well, this 15G is trying to do it, and the perpendicular distance from the line of action of the force to A is 1.5 meters. So I can say that 15G times by 1.5 is my clockwise moment, and I'm looking now for my anti-clockwise moment. Okay. Now, my anti-clockwise moment, you can probably see, if I go to A again, what's causing it to want to rotate anti-clockwise? It's this tension force here, which is not acting perpendicular to that line there. So what I'm actually going to do, which is a little bit different to how I've done it before, but hopefully it'll be clear, is I'm actually going to consider what is the magnitude of that force there, which is the vertical component of the tension, which is going to be T sine theta, because T would be the hypotenuse, opposite, so it's sine, T sine theta, and I'm just going to refer back to the question, have I been told the angle? No, I haven't, but I have enough information to work it out. Now, let's just consider this here. This is a 3 meter length. I've been told that this length is 4 meters. So what I can do, and I'll draw this over here as a separate triangle, is if the length of the beam is 3 meters and the distance there is 4 meters, then I can calculate using Pythagoras that the length of the inextensible string must be 5. The reason I'm doing this is because I want to know things about this angle theta. And what I know is that I can say, okay, well, tan theta, opposite over adjacent, but I want to know sine theta here. So sine theta is opposite over hypotenuse, so I can calculate from this triangle that sine theta must be 4/5. So when I now say with my moments equation that T sine theta times by 3 is the anti-clockwise moment, I now know that sine theta is 4/5, so I can say that I've got 22.5 G, that's multiplying 15 by 1.5, is equal to T, sine theta is 4/5 times by 3, so 4/5 times by 3, I've got 2.4 T. So if I divide 22.5 G by 2.4, I get my tension to be 91.875 newtons. Sure. Right, tension calculated. Right, B, calculate the magnitude and direction of the reaction force at A. Now, if you weren't sure about hinges, this is a massive clue because it's talking about direction. When have we ever considered the direction of the reaction force before? It's always been perpendicular to the surface it's resting on. But with a hinge it's different, magnitude and direction. But the strategy we adopt is the same. It's the same as we do with all the statics. We're going to resolve vertically and we're going to resolve horizontally. So resolving vertically, let's refer back to our diagram. Force acting up, we've got T sine theta. Force acting down, we've got 15G. And we've got another force acting up here, which is the reaction at Y. Okay. So T sine theta plus the reaction at Y is equal to 15G. Now, I've just worked out that T is 91.875. I know from my triangle earlier on that sine theta is 4/5, plus the reaction at Y is 15G, which as a number, 15 times 9.8 is 147, which is great snooker. 91.875 times by 4/5 is 73.5. Which means the reaction at Y is 73.5 newtons, subtracting 73.5 from 147. So that's found me the vertical component of the reaction at the hinge. I'm now going to find the horizontal component of the reaction at the hinge. So I'm going to be resolving horizontally. Okay. Right, looking horizontally then, I've got the reaction at X, which is acting horizontally, and then here I'm going to have the horizontal component of T. So if this was T sine theta, then I'm going to have T cos theta here. So my reaction at X is going to be equal to T cos theta. Now, let's just pause a minute. You might be thinking, hang on a minute, why is he ignoring that force arrow there? Because surely there'd be a force going like that as well. That force is not acting on the beam, that force is acting on the wall. So this force here does not contribute to anything going on to do with the beam. Reaction in the hinge, where the beam is inside the hinge, I'm not interested in that force for this calculation. In the same way as when I did it vertically, I wasn't interested in any vertical component of this force here. So if you haven't thought about that, don't worry about it. So I have the reaction at X, which is equal to T cos theta. I know that T is 91.875. Cos theta, I haven't explicitly worked out yet, but if I go back to the triangle that I drew earlier on, cos theta, adjacent over hypotenuse, is going to equal 3/5. 3/5 there. So if I do 3/5 of 91.875, I get the reaction X, the horizontal component, to be 55.125. However, let's look at the question. It's asking for the magnitude and direction. I don't have that yet. I have the horizontal component and I have the vertical component. So what I now need to do is I need to say, okay, the horizontal component is 55.125 and the vertical component is 73.5. So I need to draw a triangle, I need to crack out the Pythagoras here. So, horizontal component is 55.125. Vertical component is 73.5. That angle alpha is what I'm going to try and find. The magnitude is the size of the force, which is the same as this value here. And the direction is going to be the angle alpha. So hopefully you're happy that the magnitude of the force, we would do Pythagoras on this because we are working out the hypotenuse of a right angled triangle. And so if we work that out and square root that, it comes out as 91.875 newtons. And I hope that makes you as happy as it makes me. Now, the direction, I'm trying to find the angle alpha, so I'm saying that tan alpha 73/5, 73.5 I should say, over 55.125. I wonder if you believe me when I tell you that that simplifies to 4/3. So tan alpha is 4/3. So using inverse tan of 4/3, we get 53.13. So the direction alpha is 53.1 degrees to 3 significant figures above the horizontal. So key point for this is, if you have a hinge, then you have to consider that at the point where the hinge is happening, there is a horizontal component of reaction, there is a vertical component of reaction, and you may be asked to find the resultant of that, the magnitude and the